So in this lecture, I'd like to present a couple of ideas from classical geometric dynamical systems theory that we are going to rely on as we go through more and more complex systems, meaning systems with more and more complex dynamics, and in particular, what we call asymptotic dynamics. And some of this you have seen probably in previous classes, or if you have, if you've read some of the standard books on dynamical systems theory, you have this notion. I do want to present elements of this in the way that couples here and there with the operator theoretic approach that we are going to take, but it's necessary for us as some aspect of the background and review. It's an interesting fact that I would believe a fortunate fact for the dynamical systems community that if you take an autonomous dynamical system, x dot is f of x. Again, I'm always going to assume existence and uniqueness, if not stated otherwise, or asked a question about systems that don't have existence uniqueness. And f is in some smoothness category. Often these systems possess very curious simplicity when time goes to infinity. So they settle asymptotically as time goes to infinity on perhaps a fixed point, some equilibrium where that can be easily identified by asking that f, the vector field at that point, x equilibrium, is equal to 0. We have more complicated things, periodic orbits, equivalent to what we call a limit cycle, where the dynamics, asymptotically speaking, so there is a trajectory that has this periodicity, x of t plus capital T is equal to x of small t. I did notice in the meantime that I labeled a map, discrete map, with capital T as well. So please don't confuse the two. This is meant to be a period. Or we can have what we call a limit torus. So now the dynamics on that could be quasi-periodic with n frequencies. So not a single frequency. So the frequency in the case when you have a limit cycle would be 2 pi over the natural frequency would be 2 pi over the period. Here you could have n natural frequencies, omega 1 to omega n, that are independent. And the independence is meant in the following sense. There are no integers such that the sum from 1 to n over these frequencies multiplied by those integers is equal to 0. Let me give you a simple example so that we can understand it a little bit better. Let's suppose that I did find two integers, k1, omega 1 plus k2 omega 2 is equal to 0. In that case, I would actually have, if I divide by omega 2, I would have omega 1 over omega 2 is equal to minus k1 over k2. Right? And remember, the integers can be positive or negative, but the point here is that the ratio between omega 1 and omega 2 is some integer ratio. And so what that means really is that when you consider the motion, yes, the system could loop around quite a bit, but ultimately it's going to return somehow and continue along the motion it was doing before, right? So in this case, you would have motion with frequency, let's say omega 1 in this direction, and then motion with frequency omega 2 in this direction, and the thing would loop, I don't know, 5 times in omega 2 and then once in omega 1 and come back. But this is really then a periodic orbit. what happens when you have this non-resonance, so if you don't have any integers such that this is true, is you would have dense winding on a torus, yeah? So the every trajectory would cover the torus in a dense manner. It wouldn't quite pass through every point, but it would pass arbitrarily close to every point, as described in the appendix on topology that I put in. So so these are the simple type of attractors that the dynamics can settle in, and here, you know, pictorially, here would be systems that settle to a fixed point. Here would be a system that has a limit cycle. Here is that periodic orbit that's a limit cycle, and you ultimately lead to the limit cycle. And here is a torus where, you know, any orbit from the outside would just kind of wind around and keep going around the torus in an approximately dense manner. The trajectories on the torus themselves would be dense, would be dense on the torus. Now, of course, there is more complicated stuff, but it took us an enormously long time to discover it. The first time we got an inkling that there are attractors in physical systems. There are people before Ed Lorenz who saw it in a physical system. I should also mention that Ueda in Japan, in Kyoto, saw dynamics that is not any of the ones that I've just mentioned in 1961. That was not published. Lorenz's discovery was not published in 63, but if I remember correctly, in 69 or 70. So it took a long time to publish these discoveries because the scientific community was hesitant to accept that there might be anything else than this simplicity, which in retrospect is a little bit odd, isn't it? I mean, why, you know, a philosophical question might be, why does the dynamics become simple in these types of systems very often? Why does it go to an equilibrium or a simple thing like periodic motion or quasi-periodic motion? But we'll leave that question aside and not discuss it further. So let's go back to the technical aspects. What I mean by saying the dynamics is going to settle, it just means that starting from some initial condition x0, as time goes to infinity, one approaches the set A. That's the notion of convergence. So let's suppose you have some set. Let's say it's actually a limit cycle, and you have some trajectory that is starting from x0. And you want to know that the distance between this trajectory and the limit cycle goes to 0 as time goes to infinity. If you had a fixed point, this would be quite easy to define, right? You just define, we are in a plane, you just define the distance between the point on the trajectory and the fixed point, and you would have your measure for convergence. For a limit cycle, it's a little bit more difficult, right? Because as this trajectory goes around, it never quite approaches any single point. It approaches the set. So you need a notion of convergence to a set. That's not very hard to come by. You could introduce a measure of the distance by first knowing or having in your hands the notion of distance between 2 points. For example, in a plane, you could just use the ordinary Euclidean distance. So just the distance that is defined by taking a straight line between 2 points and measuring its length, and that would be your d. And so now to measure the distance between this point and this whole set, you do that for every point on the set. And then you find the point on the set for which this is the smallest, and you say, the infimum over all points in the set Y, so this is my set Y, the distance from my point X, I measure the distance to every single point, and the distance from a point in the set is going to be the minimum of all these distances. Well, infimum in general, because the set, you know, the minimum itself might not exist. For example, if the set is infinite, yeah. or open for that matter. So this is a closed set. Every single sequence in that set converges. All right. So now that we have first what we call a metric, which is a way of measuring the distance between 2 points, and this notion of distance between a point and a set, we can define convergence or asymptotic behavior by saying, okay, the trajectory asymptotes to a set A if the distance between the trajectory and the set A goes to 0 and time goes to infinity. That's the idea. And it's clear that in order to go through this whole business, we do need, to have some such metric. A metric on a circle, just to mention this, is a very different thing to decide. So take a circle, and so then say, what is the distance between this point and this point? And you could say, surely, well, it's the arc length between these 2 points. That's one way of measuring the distance, fair? But which one? I mean, you could take this arc length or that arc length. So what is called the geodesic distance is defined by taking the minimal arc length here, right? And that is a proper quote unquote metric. I'm pointing this out so that you realize that it's not always completely trivial to say, oh, there is a metric on the space. And in a simple case, that's really, of some importance in mechanics, of just an object that is a circle. That is you have to work just a little bit. I mean, I'm not saying it's not obvious. I'm just saying it is not entirely trivial like the Euclidean distance. All right. So once we have a metric, we can measure the distance between trajectory and the set. And now I need to work a little bit further and talk about asymptotic stability. So asymptotic stability is of a set A is defined by asking for an open set B such that A is inside B. So here is B, and B is open. So this boundary of B is not really in B, that's just denoting the outside. And here is my set A, and so A is a subset of B, and for any initial condition in B, the distance between the trajectory starting from that initial condition and A goes to 0. That's asymptotic stability. So now you have a bunch of initial conditions such that they start in an open set B and they converge down to A. And I'm going to ask for 2 more things. I'm going to ask that A is invariant, right? So A needs to be an invariant set. So we had that before. So there is a time, if we pick any time t in R for a continuous time system, then ST of A is A. I'm assuming existence uniqueness, and to Matthew's point, I'm not now asking for minus t. I actually went forward this time, right? So I reduced a little bit the generality. And the condition 2 is something new, that A is topologically transitive. I don't think we had this in the previous classes. I might have mentioned it in 215. So this means that if you take any 2 sets, C and D, that are open, the topologically open sets, think on a circle, just intervals. So here is C, here is another interval D. The requirement is that for some time tau, if I take the image of C under the dynamics of this flow, I'm going to intersect D. So it's very easy to see, for example, in this circle, I just have a rotation, right? So I take this initial interval, and the way the rotation on the circle is going to take it over is at some point, at some time t, s tau, at some time tau, s tau c is going to intersect D. And that has to be valid for any sets that I have, C and D. So that's called topological transitivity. Any initial set, no matter how small, and any final set, no matter how small D, are ultimately going to intersect each other. So if we have this asymptotic stability and we have these two conditions, we are calling the resulting set A an attractor. I should warn you that there are different notions of attractor, and there are papers. I'm going to post one that is a favorite of mine on the class webpage, in which different notions of attractor are put forward. And even in this class, at some point, I'm going to talk about what is called the Miller Attractor, that depends more on some measure theoretic concepts and not metric concepts. But for now, and you know, predominantly dynamical systems, this is okay. All right. Yeah, don't hesitate to ask questions. Just raise your hand on Zoom. You probably know how to do that, and ask me. We can interrupt the flow. There's no problem with that. Okay, so now we have the notion of attractors in hand. Before we proceed, let me say the following. It is interesting that some invariant partitions of the state space arise in dissipative systems from properties of the attractor. So you would say, oh, I have a limit cycle. I have a limit cycle. Draw this for a second. And I'm looking, so let's say it's a limit cycle. Almost every initial condition converges to it. The only one that doesn't is the fixed point at the origin. But if we exclude that from our considerations, everything converges to this limit cycle. And you'd say, if I'm looking for partitions, I can't just look at the limit cycle, right? And so let's look at an example, and you will see that there are certain important partitions that are really informed by the dynamics on the limit cycle. And they have to do with the notion of phase, in particular nonlinear phase. You're probably very much used to the linear phase notion. Those of you who have taken my previous class, graduate class, are familiar with the notion of nonlinear phase and isochrones. So let's review a little bit of that. So take this two-dimensional dynamical system. R dot is R times 1 minus R squared in parentheses, and then theta dot is omega. So in the theta direction, this is my theta direction, we have pure rotation with angular speed omega. And then in the R direction, if R is bigger than 1, so this is R is equal to 1. If R is bigger than 1, then we have a decay in R. So R dot is less than 0. If R is less than 1, then we have growth. And that's reflected in these trajectories. They spin, and if they're outside of R is equal to 1, then they decay towards the limit cycle. And if they're inside, they go towards the limit cycle. That's the idea. And so every initial condition, except for R is equal to 0, asymptotically converges to the circle R is equal to 1. So our set A is this from our previous definition. I already in a sort of hand waving way, told you that A, this circle here, is topologically transitive. I'm also indicating here that it's asymptotically stable because the set B I can obtain by taking the whole plane except for this point in the middle, and that's an open set, right? If I just take the point in the middle and take the rest of the plane, everything converges towards the limit cycle. Therefore, this thing is an attractor. And so now what is interesting is that the angle theta here coordinatizes the points on the circle. And for every initial condition with the same theta 0, let's say we start with some theta 0 here, right? We start with some theta 0 here. All the initial conditions on that ray are going to be doing exactly the same thing in the angular direction, yeah? Exactly the same thing. They're going to be rotating with the same speed, pretty much the solid body rotation there. And therefore, all of them are going to asymptotically come together and converge to the same trajectory on the circle. And that trajectory has what is called an asymptotic phase. I'm going to go into the subject of isochrons in gory detail later on. You will see that these rays that I've just identified are actually, they have a name to them. They're called isochrons. They're the points of the same what is called nonlinear asymptotic phase. But the point that I'm trying to make is that the theta on the attractor is informing me about the dynamics and interesting points of the attractor. So the asymptotics are defining something in the whole basin of attraction. And that's interesting because you can understand something about the dynamics in the transient part of the dynamics from understanding how the asymptotics are behaving. So as I mentioned, this partition into these rays of constant angle is the partition into what is called isochrons. And what is interesting there is consider now the level sets of this function. F of r and theta is e to the I theta. So note the function doesn't depend on r. The dependence on r in this case is unnecessary in the theta direction, the reason being that the dynamics doesn't depend on r, right? So this is the function that we chose. And so consider the time evolution of this function f. So let's take the time derivative. We obtain I e to the I theta, theta dot, and theta dot is omega. So then f dot is I omega e to the I theta. E to the I theta is f. So I get f dot is I omega f. So this function, this complex function, is an eigenfunction. Remember, the eigenfunction of the Koopman operator satisfies phi dot is lambda phi. That's an eigenfunction. So f dot is I omega f. So if lambda is precisely I omega, I found an eigenfunction. That eigenfunction is complex. And it's level sets, but we have to be careful here. You know, one has this natural tendency to think about the level sets as like, oh, you take a real function, you take its constant value c, and you find all the points on which that function has value c. That would be a level set, yeah? But here, we're looking for the level sets of the constant function. This function maps points in the plane into the complex plane. In fact, into the unit circle, right? E to the I theta is just a unit modulus complex number. And so this is a mapping not from the plane r theta to real line, but to unit circle. And its level sets are in fact those rays. When theta is equal to constant, yeah, that's equal to some point on the, for example, if theta is equal to 0, the point on the circle you're mapping to is 1, yes? E to 0 is 1. So that's what you get. So those are these rays of constant theta. They are the level sets of a Koopman eigenfunction. I'll show you that this is completely general towards the end of this lecture, or maybe if we spill over to the next lecture. Anytime you find a Koopman eigenfunction, you're going to find a partition. And therefore, Koopman eigenfunctions give you geometry of the dynamical system, not in the sense of trajectories, although that's possible as well, because, for example, in two-dimensional systems, the Hamiltonian that I've shown you, that splits the state space into orbits. So if you take constant values of energy, the energy itself is a Koopman eigenfunction, splits the state space into orbits, right? So you can get even individual trajectories, but more commonly, you get interesting sets that are providing interesting geometrical and physical information. In this case, that physical information is what is the phase starting from some initial condition? What is the asymptotic phase of the system starting from some initial condition? All right. So this is how Koopman eigenfunctions get informed by asymptotics, and how they provide us, how then in turn they provide us with partitions on the full state space that are determined by the asymptotics on the attractor. So that's interesting. So one other notion that I will use is that of a quotient space. The quotient space is this idea that if you have, for example, a set of this form, and then you have a bunch of lines whose union gives you that set, right? Then you can parameterize those lines by some coordinate. Let's call it x. And while your original set is two-dimensional, this parameterization is one-dimensional. It loses information. In machine learning, it would be, an encoder with a loss, because the only information that you can get back is if you know x, you will know a set of points in the set that corresponds to that. So what we say in mathematics is that this interval here, a to b, and a and b are the initial and final value of x that we're parameterizing this with. So this interval ab is a quotient space of the original space M that you obtain by mapping a whole line of points into a single point on the interval. That's the idea of the quotient space in general. So the quotient space is obtained by taking a map and taking a bunch of points, for example, all the points in an element of a partition into a single point. That's the idea of the quotient space that we're going to be using further. We're going to be using further as we go. So the next thing up is those simple types of asymptotic dynamics that lead to attractors like fixed points, limit cycles, periodic orbits. You can easily connect those with very practical considerations, like if you have an oscilloscope in the lab and you hook up your system to that oscilloscope and you're looking at an output of the oscilloscope, you can tell what the asymptotic dynamics is. In particular, Fourier analysis will do. So let me show you some oscilloscope outputs, right? So here is a signal. So this is time. This is, let's say, position or voltage. And this is the spectral analysis that you'll get. So you'll get a peak at the base frequency, and then you're going to get twice that base frequency, 3 times that base frequency, 4 times that base frequency, if you have a nonlinear signal like this, if it's not sinusoidal, right? The Fourier analysis is going to tell you that there are harmonics of the original oscillation. You see that they decay. The faster the harmonic is, the less quote unquote power it has in this representation. But if you were an experimentalist and looking at this output of the oscilloscope, you would pretty much immediately tell me, if you knew dynamical systems, this is a system that limits cycles asymptotically. Yeah, there is. So, and the reason for this is that any solution of the dynamical system on the limit cycle is periodic. And if it's periodic with period capital T, then it can be expanded in a series like this with natural frequency omega being 2 pi over capital T, yes? So AJs are the coefficients. This could be a multi-dimensional trajectory, but finally it settles on some limit cycle. Here are the coefficients of the Fourier series. Here are the e to the ij omega t. So the time coefficients, yeah? So the system evolves harmonically in time. These are complex exponentials with natural frequency omega. So if you see this, I have a limit cycle. If you have a limit cycle, you're going to see this. You immediately identify your system from that. There's another type of system. Let's say that you have 2 frequencies in play. Earth around the sun, moon around the earth. 2 different frequencies of oscillation, yeah? So you have a system with 2 frequencies playing. Then you might see on your oscilloscope a signal, a representation like this. So this is your signal, and you see pretty much 2 frequencies. One of them is fast, and the other one is this one. Yeah? And the way that's represented in Fourier space is you have F1, that's the slow frequency, this one, and then F2, that's the fast frequency. This particular experiment is in gigahertz, and that's actually voltage. But then besides F1 and F2, you're also going to have a peak at F2 plus F1, F2 minus F1, 3 times F2 minus F1, 5 times F2 plus 3 times F1, and any combination of that sort. That's the equivalent of subharmonics here, right? So when you have 2 frequencies, you can recognize that you have 2 frequencies, but basically trying to identify whether you're seeing peaks at the appropriate. So you need to identify 2 base frequencies, and then the frequencies that are integer combinations of those. This stuff here, that's the noise floor, right? This stuff is noisy, but the peaks are the things that matter. Here's the noise as well. So in the case of quasi-periodic attractors, you can expand in multi-frequency Fourier series. So K is now a vector of integers. Omega is a vector of natural frequencies. And I'm asking that they're not resonant. That's the condition that I had before. Remember, I asked that omega 1 divided by omega 2 are not represented as some ratio that is integer ratio. So then I'm going to call this a quasi-periodic signal. The quasi-periodic signal is interesting because it never repeats itself. It looks very simple. It looks deceptively like this single frequency signal. But in fact, if the ratio of frequencies are, if the ratios of frequencies are not rational, then despite the fact that this might look like it repeats, it doesn't. It always comes maybe very close to an original condition, but it keeps innovating a little bit and taking the signal to places it hasn't been before. And the major point is that if you're seeing this on an oscilloscope, you have a limit torus with 2 irrational frequencies. And if you have a limit torus with 2 irrational frequencies, you're going to see that on the oscilloscope. The point is, you can recognize your system. The reason why I'm introducing it this way is that when you have dissipative systems, it's a little harder, right? Because you the Fourier analysis is only going to tell you something about the asymptotics. The Koopman operator theory is going to lead us to an idea that is pretty much going to be the same as an oscilloscope idea. It's going to lead us to an idea that tells you, when I look at an output of data analysis, I'll be able to identify the system, just like I did now. Oh, that system has a limit cycle. So from Koopman operator theory, I'll be able at some point to say, oh, I have a system, with a limit cycle with certain type of asymptotics. So it's a pretty clean and nice extension of these Fourier ideas. And in modern data science applications of Koopman operator theory, it's actually quite important. So as we go, we will build these ideas for different types of systems that have fixed points, limit cycle attractors, quasi-periodic attractors, chaotic attractors, and we're going to discuss the type of the spectrum, the type of eigenvalues that each of these systems have, if they have them. Like chaotic systems actually typically will not have any eigenvalues, with the exception of some that might have some hidden order within that chaos. Look up the map x prime is equal to minus 2x, and you will see that in the lecture I said, oh, this has an eigenfunction and eigenvalue. So sometimes even in chaos, you have this very hidden order and eigenfunctions. But in general, things like Lorentz attractor that I'm going to discuss next, they don't have eigenvalues. They have some more complicated version of the spectrum, but the major point stands. I look at the spectrum of the Koopman operator, and I'll be able to recognize both the dissipative and the transient, the dissipative or the transient parts of the dynamics and the asymptotic parts that I was able to say something about using Fourier analysis before. So from this perspective, the Koopman operator theory, for an experimentalist or data scientist, can serve as a clean extension of Fourier analysis and be useful in that context.